Okay, everyone. Sorry about canceling class last time, but I wasn't feeling well, so life happens. How much time do you all think we need to talk about the exam? We have an exam on Thursday, right? I sent out the review. I sent out the solutions to the review. So how much time should I save at the end of class for us to discuss it? 15, 20 minutes? Okay. Will you all make sure that you stop me when we get to that point? If I get too far into it, right? About, what, is that right? About 2:20 or so. Don't let me get past 2:20. All right. So we're going to try and get caught up, but I don't want to force it. I don't want to speed it up too much. We need to finish up the graphing of tangent, cotangent, cosecant, secant, cotangent. Tangent, cotangent, secant, and cosecant. We haven't done that yet, right? We did talk about tangent, but not enough for us to be ready to do it on the test. So let's just pick up there. We're going to talk about tangent. The graph of y equals tangent x. So what are the main things you need to know about tangent x? Just like with sine and cosine, there's important points that you should be using to graph a tangent function. Yes?
Just finishing off 7.7?
7.7. Yes. 7.7. Yeah, we're in 7.7 here. So you know with sine and cosine, right? Maybe we should start there. With the sine graph, we should all be comfortable with the idea that it goes like this. Right? That's the basic sine graph. And then the cosine graph is like this. It has the same important points. Right? It has the same important points. 0, pi over 2, pi, 3 pi over 2, and 2 pi. And so that's why when we're graphing sine and cosine, first thing we do is we set the argument equal to 0, equal to pi over 2, equal to pi, equal to 3 pi over 2, and equal to 2 pi. Right? That's the kind of approach we've been taking with it. So that's how we do these. For tangent, what we need to know is that all tangent functions look like this. They have vertical asymptotes all over the place, but the ones that we're most concerned with are the ones at pi over 2, negative pi over 2, and that the graph goes through 0 and then looks like this. Okay? So if both sine and cosine have 5 important points for us to graph a sine and cosine function, if we need to look at 5 points, over here we actually need to look at 3. There's 3 important things we need to be looking at. What happens at negative pi over 2, at 0, and at pi over 2. So let's do an example of graphing a tangent function using just what we know about the basic tangent function and see how changing things, changing the argument and putting negatives and numbers, how it changes the picture. All right, so let's go with 3 tangent, and let's go with 1/4 x. So if I wanted to graph that, what I would do is I first need to know, okay, I know basically it looks like this, right? But I need to figure out where do the vertical asymptotes occur, and then where do I get 0? Where do I get that x-intercept? So I'm going to take the argument, just like we did before, 1/4x, x, set it equal to negative pi over 2, take 1/4, can't write today, x equals 0, 1/4x equal pi over 2. Right, so I'm going to solve those 3 equations for x. So on this first one, I would multiply both sides by 4. What would I get if I multiply both sides by 4?
X and negative 2 pi.
X equals negative 2 pi. Good. And this one, if I multiply both sides by 4, I get x is 0 still. And on the last one, if I multiply both sides by 4, I get 2 pi. Is that okay, everyone? Not showing that work? That's okay. So now I'm going to go graph. So when I go to graph this, I know that this middle point right here, this middle point should correspond to where I have 0 for my graph. So I know I should go through here. But instead of one of the vertical asymptotes occurring at pi over 2 and the other one at negative pi over 2, they're going to occur at 2 pi and negative 2 pi. So I'm just going to put over here 2 pi, over here negative 2 pi. I'm going to draw vertical asymptotes or dotted lines here. And then I'm going to go and try and draw my tangent function. All right? Now, this number 3, back with sine and cosine, what did the number in front do with sine and cosine? That number is the amplitude, right? It helps us get the amplitude. And that tells us how high and low the sine function goes, right? A 3 in front of a tangent function, what it does is it does the same thing. It stretches it out. It makes it taller. But since the graph is already going like this, up to infinity, it stretches it out, but the shape is basically the same. So it's kind of like this. If this was tangent, 3 times tangent, we'll just take each point and multiply by 3. So it gets stretched up like this. But do you see it's basically the same shape? Still does the same thing? Yes? So that's my graph. What do you think would have happened if this would have been a negative 3? That would have flipped the whole picture over the x-axis. So instead of going up here, it would have gone down. Instead of going down here, it would have gone up. Make sense? Any questions? So for tangent, you take the argument. You set it equal to negative pi over 2, 0, pi over 2, and then you plot those points and do your verticals on the ends. The middle point will be your x-intercept, and then you draw it. Now keep in mind that this graph does repeat itself. Just like sine and cosine had periods, this has a period as well. How big is this period? What's the distance from here to here? 4 pi, right? 2 pi is from here to here, 2 pi from here to here. So let's see. I would have to go out to 6 pi before I get my next period, and then right in between those is my 4 pi here. Do you see it's 2 pi to the left, 2 pi to the 2 pi to the left, 2 pi to the right, and then I would have the same picture, and then it just keeps repeating itself as I go both left and right forever. Okay? No questions? Let's do a cotangent. So for cotangent, the difference is that when you look at the basic picture of cotangent, instead of having negative pi over 2 and pi over 2 where you have the vertical asymptotes, the vertical asymptotes on cotangent occur at 0 and pi. And then right in the middle at pi over 2 is where you have an x-intercept. So you have a vertical asymptote over here. And then right here you have a vertical asymptote through the y-axis. So like that. And then it looks like a tangent function, except it's flipped over. So it goes up on the left and down on the right. That's what a basic cotangent function does. And of course, it repeats itself on the sides. So let's go try and graph a cotangent function. And let's do 1/10 cotangent of 5x. Let's do that. Am I? Make sure. Did I hit record? What's that? Can't tell. Hold on. Sorry. I see a red dot, but it's not. Yeah, it is going. Okay. So what do you think I'm going to start with? What am I doing? Yeah, but tell me what I'm doing. Start the argument and set it equal to 0, pi over 2, and pi. Those are the three important points for cotangent. So I set x equal to 0. Sorry, not x. 5x equal to 0. 5x equal to pi over 2. And 5x equal to pi. And then I solve each of these for x. Why am I using these three? Because it's cotangent. If it were tangent, it would be negative pi over 2, 0, and pi over 2. If it was sine, it would be 0, pi over 2, pi, 3 pi over 2, 2 pi, right? All right, let's solve these. Divide by 5, right? Still get 0 there. Divide by 5 here, pi over 10. Divide by 5 here, pi over 5. Now I go to my graph. I don't like that. Okay, so I'm going to plot these points. Here's 0. Let's see, pi over 10, I'm going to put it here. Pi over 5 is here. And then I need to know what I'm putting at these points, right? Because it's a cotangent function, I know the middle point is where I have the x-intercept. And I know at the two edges is where I'm undefined. And then it's got to look like a cotangent, so it's going to be like up on the left and down on the right, as long as it didn't get flipped over. Did it get flipped over? No, there's no negative there. But it is multiplied by 1/10. What do you think that does? It compresses it down, like it makes everything shorter. It's kind of hard to show that on a cotangent function. But the idea would be this. If this is what it would be, if this is what it looked like if it was just cotangent, then 1/10 of it would be, you're basically scaling all of these by 1/10. So they're not as tall as they used to be, right? So our picture is probably going to be more like this. But if you're just graphing this on a test, that's hard for you to show me. So I'm really more concerned about, are you going to get your vertical asymptotes in the correct place? Are you going to get your x-intercept in the correct place? And does the left side go up and right side go down? That's the thing I'm more concerned about. Questions? Yes?
Why did you pick those 3 points? Would they not have been regular 5?
Anytime you're doing a cotangent function, those are the 3 important points. So when it's sine and cosine, we have the 5 points, right? But when it's tangent and cotangent, we only do 3 points, and they're different for tangent than they are for cotangent. Yeah? All right, that's it. That's how we graph tangent and cotangent. We good? We're going to move on. We're now going to talk about what secant. Well, let's do cosecant first. So what does y equals cosecant x look like? Well, we first need to remember what this is, right? This is 1 over sine, isn't it? Just the reciprocal of sine? And don't we already know how to graph sine? I mean, theoretically, we know how to graph sine, right? So I'm gonna graph the sine function over here for us. And let's see if you can follow what's going on here. I'm going to graph in blue the sine curve. That's just one period of the sine. It goes, what, 2 pi here. This is 3 pi over 2. This is pi. This is pi over 2. And this is 0, right? And it goes up to 1, and down here, -1. That's what sine looks like, right? So what would 1 divided by sine look like? So let's just start going to some points. Let's look at 0. What if I plug 0 in here? Sine of 0 is 0, right? You can see from the graph, sine of 0 is 0. So what's 1 divided by 0? What's 1 divided by 0? It's undefined, right? So right away we know we have a problem, right? The cosecant function at 0, if I go to graph it, it's undefined. That means I'm going to have a vertical asymptote here. Where else would I be undefined? The cosecant. Where else would it be undefined? At pi also, right? Anywhere where the sine function hits the x-axis, right? Anywhere where the sine function gives me a 0, right? Anywhere where the sine gives me a 0, 1 over sine is going to be undefined. So I should have a vertical asymptote here. Do y'all get what I'm saying here or not? I'm trying to draw cosecant, and I'm using the graph of sine to get an idea of what's happening to the cosecant function. What about here at pi over 2? At pi over 2, what's the value of sine at pi over 2? 1, right? So at pi over 2, if I plug in pi over 2 into this, I know I get a 1 on the bottom. 1 divided by 1 would be 1, right? So my cosecant function, which I'm drawing in black, actually this point does live on the cosecant function, doesn't it? What about right here? What about if I go to 3 pi over 2? If I plug 3 pi over 2 into sine, what do I get? Into sine? -1, right? So imagine you plug 3 pi over 2 right here. You get 1 over -1, which is -1, right? So the cosecant function should also be here. Do y'all see why those 2 points are on our cosecant graph? Yes? No? Yes? Y'all are giving me this look. So we're clear? We have vertical asymptotes here, here, here. We have this point and this point are on that function. But what about the rest of the function? So this is where I really need you to think, all right? What if I pick this point right here? I don't even know what angle this is. What if I pick that angle right there and I plug it into the sine function? Right? So whatever that angle is, it's a small angle, right? I plug it into the sine function, I'm going to get an answer out, right? Sine is how tall that is. So is this number that comes out, is that a big number or a small number? Here's 1, right? That number got smaller, right? So what happens if I take the number 1 and I divide it by a small number? What do you get? A big number, right? Everyone agree? Take the number 1 and divide it by a small number, you should get a big number. So if I go to try and figure out what's cosecant doing here, it should be a number that's kind of big. And what happens if I get even closer? Like what if I take that point right there? That's a really small number, right? And 1 divided by a really small number should be even bigger, right? So now I have another point on my cosecant graph that's even taller, right? And the closer I get to 0, the smaller the number gets, and 1 over that number should get bigger and bigger and bigger. And so with that idea, does it make sense that the left side of this should look like that? Like a vertical asymptote? Yes? What about if I start picking points here, like this one, and that one, and that one? If I plug those into this, 1 over those numbers, as I move to the right here, my answers are getting bigger or smaller when I plug it into there. Bigger, right? These numbers are getting smaller. The sine values are getting smaller. 1 over sine should get bigger. So do y'all see that it should do like the same thing as I go this way? Doesn't it kind of look like a parabola a little bit? It's not a parabola though. The big difference between that and a parabola is that these two curves have to live between these two walls. Where with the parabola, a true parabola, it spreads out forever. There's no walls that stop it. Here we got 2 vertical asymptotes that look like walls. Questions on that? What you see in black there is part of what cosecant looks like. All right? Let's go over here. This point we know is on cosecant. What do you think happens as I start to draw it this way? Do you think I go up, like another thing like that, or do you think it goes down? What do you think? It's going to go down. Let's think about why, though. If you plug in values into the sine function, this is a negative number, isn't it? That's a negative number. And the closer you get to this vertical, so as I move further here, right, those numbers are getting smaller but negative, aren't they? Smaller but negative. So if I take the number 1 and I divide it by a small negative number, I should get a big negative number, right? And big negative means that my graph should start going negative but getting big. So it does this, and then it does this. And then sine's going to repeat itself, isn't it? Oh, terrible. Sine's going to repeat itself like that. And everywhere that sine hits the x-axis, we're going to have a vertical asymptote. And at every peak, right, we're going to have another one of these little u's. And at every valley here, we're going to have another one of these u's like that. And it's going to go forever in that direction and forever in this direction. You with me? And if we take out everything, that's the graph of cosecant x. That's the graph. Okay, all that other stuff was just to help me build it up, you see? But that's the graph. So what I'm telling you, really, by doing this example, is that in order to graph a cosecant function, all you really have to be able to do is graph the sine. If you can graph the sine function, then all you're going to do is just draw these little u's on the top and bottom of the peaks and valleys of the sine function. All right? Let's do an example. On exams, a lot of times I won't even ask you to graph a sine function. I'll ask you to graph a cosecant function because you have to be able to graph a sine to do the cosecant. Now on this test, because of the way things landed, you're going to see me ask you to graph sine and cosine. All right, so here we go. Let's sketch y equals -4 cosecant of 1/2 x. So what I'm going to do here, in order to do this problem, what I'm going to do is I'm going to, instead of looking at this, I'm going to look at the graph of -4 sine of 1/2 x, like that. I'm going to look at that graph. I'm going to draw this graph, and then I'm going to just throw the u's on the top and bottom. Does that make sense? That's all I'm going to do. So to graph this sine function, I'm going to look at it and say, okay, my amplitude is 4, right? I've got a negative here. That means it gets flipped over the x-axis. And I need to set my argument equal to the 5 different points, right? So let's do our 5 points. 1/2 x equals, what are the important points again for sine and cosine? 0, pi over 2, pi, 3 pi over 2, and finally 2 pi. Right? So you're going to set your argument equal to those. And solve. All right, here you get 0. Here you get pi. Here you get 2 pi. Here you get 3 pi. Here you get 4 pi. Once I have those points, I'm going to graph the sine function. Now I'm going to graph this in a different color. I'm going to do it in blue because my final picture is going to be the cosecant picture. I'm going to do that one in black, all right? So I'm going to graph this one in blue. So let me try and see what I'm going to do here. I've got these important points. Let me plot them. I've got 0 here. This is 4 pi. This is 2 pi. This is pi. This is 3 pi. Now I know, because this is a sine function, that I have three important x-intercepts, right? Three important x-intercepts. They happen here, here, and here, right? And then the graph is going to go, normally it would go up to 4, down to -4 because the amplitude. Normally it would go up, and then down, and then back, right? But it's been flipped over, right? It's been flipped over. So instead of going up and down and up, I'm going to draw it down, up, and down like that. Right? That's the picture. Questions on this? Okay, once I'm here, I'm going to draw my vertical asymptotes. Remember, anywhere the sine function is 0, the cosecant function will be undefined. So at this x-intercept, I'm going to draw a vertical. At this x-intercept, I'm going to draw a vertical. And over here at this x-intercept, I'm going to draw a vertical, like that. And now I'm ready to draw the cosecant function. So all I'm going to do is go to this valley, this bottom point. I'm going to draw u out this way and this way. Keep it in between the verticals. And then over here, I'm going to draw u up and up like that. Keep it between the verticals, and I'm done. What you see in black there is the cosecant function. Questions? You can make this like dashed, since you may not have colors. Like on a test, you can make that dashed, or you can erase it, whatever you want to do, okay? Just remember that the function itself is just the black part, right? All this other stuff is just to help us. Yeah? Okay. All right, let's keep going. What about cosecant then? I mean, sorry, not cosecant, secant. What about the secant function? What does that look like? So if we graph secant x, by definition, secant is 1 over cosine. So you see, I'm going to do the same sort of argument that I did a second ago when I did cosecant, which was 1 over sine. I'm going to look at what's 1 over cosine. So let's draw the cosine curve first. All right, I'm going to draw the cosine curve over here. The standard cosine curve, again, 2 pi, pi over 2, 3 pi over 2. It has 2 x-intercepts here and here, right? Those are the anchor points for cosine are the 2 quarter ones, right? Not the ends in the middle, that's sine. For cosine, it's those 2. And then it goes up here to 1, here's -1. And a standard cosine function will start here, it'll come down to this point, and go back up here. So it'll look like this. Okay, that's our standard cosine. Now, same argument we just made a second ago. Anytime we get 0 down here, right, this is going to be undefined. So anywhere we have x-intercepts over here, this secant function should have vertical asymptotes. So right here at pi over 2, I should have vertical asymptote. And at 3 pi over 2, I should also have vertical asymptote. And then using the same sort of argument we did last time, if I plug in pi, I get -1, right? Plug in pi, you get -1. So if this is -1 down here, 1 over -1 is still -1. So this point, doing it in black, this is part of my secant function. And then if I move to the left, my point should get bigger but negative. And I move to the right, bigger and negative. So I'm going to have that same sort of thing happening there. You see? It's like that U shape between these 2 verticals. The thing about cosine that's weird, secant that's weird when you graph it is what's happening here to the left. So in reality, the picture goes to the left and to the right, but I'm only going to draw the right piece of it like that. And over here, I'm only going to draw the left piece of it. But just know that, I mean, it does go this way as well. And it goes this way to that next vertical that's over here and over here. But the picture that you see right there is sufficient for what we need to do, right there. Right? That's what a secant function looks like. So it's basically the same as a cosecant function. It's all these little u's, all right? Up and down. We happy? So let's do one sketch of this. If y equals, let's sketch 1/3 secant of pi x minus pi over 4. So I look at this and I say, okay, I need to graph a secant, right? Secant's the reciprocal of cosine. So I'm really going to graph the cosine of this first. So I'm really going to do y equals 1/3 cosine of pi x minus pi over 4. And so I take my argument and I set my argument equal to those 5 important points, right? It's going to kind of suck, but you know, it is what it is. So I'm going to take pi x minus pi over 4, set it equal to 0. Pi x minus pi over 4, set it equal to pi over 2. Pi x minus pi over 4 equals pi. Pi x minus pi over 4 equals 3 pi over 2. Pi x minus pi over 4 equals 2 pi. I'm going to find my 5 important numbers. That's going to help me draw my cosine. Once I draw my cosine, I'm going to draw vertical asymptotes, then I'm going to draw these little u's. All right, for this one, how about for all of these? I don't know, I'm going to do something. I'm going to see if y'all like this or not. Do y'all see that on every one of these equations, with the exception of the first one, you have a pi in every term. Pi, 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 pi. There's pi's everywhere, right? So for each of these equations, I'm just going to divide everything by pi, both sides. And won't that get rid of pi's everywhere? Won't it? Divide that by pi, the pi's are gone, divide that by